Okay, that's all well and good, but how do we go about finding a mixed strategy that maximizes the expected utility for both players? Consider this game right here, where the mixed strategy solution is not so obvious as it was in the previous one. Notice that here row has a choice between two strategies, R1 and R2. Column has a choice between two strategies, C1, C2. Notice that there's no dominance, okay? If column chooses C1, row does better choosing R2 rather than R1, 6 as opposed to -2. But if column chooses C2, row does better choosing R1 rather than R2, 1 as opposed to -3. Similarly for column. If row chooses R1, column does better choosing C1, a gain of 2 as opposed to a loss of 1. But if R chooses R2, column does better choosing C2, a gain of 3 as opposed to a loss of 6. So, no dominance, and also you'll see that there's no, if you do all the three tests for pure Nash equilibrium points, none of these points are in Nash equilibrium. So how do we go about finding the mixed strategy? Well, I put a handout onto the Resnick Game Theory book, Canvas site, that includes a derivation, a step-by-step derivation of these formulas, which are given by Resnick on page 140 of your text. You might have found the algebra a little dense to work through, so I've worked all that out for you to show you how Resnick goes on page 140 from calculating the assignments of some random probability P, 1 minus the random probability P to R1 and R2, some random probability Q, and 1 minus that to C1, 1 minus that probability Q to C2, and then based on the expected utilities using this formula for both row and column, he derives the solution to P and Q by simply laying these out as equations and solving for P and solving for Q. And again, like I say, the algebra gets a little dense, but I've worked it out for you in case you don't see exactly how to solve for P and Q as it goes on Resnick on page 145. Page 140. I've filled in all the missing steps.